So welcome to the state space method. In this lecture we will discuss about how to convert a transfer function to state space. So we have defined the transfer function, that is in frequency domain, and the state space approach belongs to the time domain. Now if we are given a transfer function, then how can we convert this to state space? So here, to convert a transfer function to state space, we first convert the transfer function to a differential equation by cross multiplying and taking the inverse Laplace transform, assuming zero initial conditions. Then we select a set of state variables called the phase variables. So phase variables, we select the output and n-1 derivatives as the state variables. So in order to select the phase variable, so we select one variable, that is output, and its derivatives, subsequent derivatives, as the state variables. So let's see, if we have a differential transfer function Ts or Gs. So we have some transfer function. This transfer function we can represent as, in terms of differential equation. So here Cs equal to Rs into Gs, and we take the inverse Laplace transform and we will find the differential equation, and we cross multiply these terms in numerator denominator and we get the nth order differential equation. So we get dny by d tn plus a n minus 1 d n minus 1y by d dn minus 1 plus a1 dy by dt plus a0y So here we can have input, so b0u. So this is a differential equation that we obtain from this transfer function and inverse Laplace. Now we have to select the phase variables, state variables, because in state space we have to represent the state equations, and so the state variables, and state variable here we select as phase variables. So phase variables are that we first select the output as one state variable, and the subsequent state variables like x2 equal to dy by dt. So here the subsequent variable is the derivative of the previous variable, and so this is called phase variable. So x3 equal to d square y by dt square, and so on. So xn equal to dn minus 1 y by dt n. So these x1, x2, x3, xn, these are the state variables or phase variables. So now we have x1 dot, that is dy by dt, and x2 dot is d square y by dt square. So here x3 dot equal to d cube y by dt cube, and here xn dot equal to d n y by dt n. So now we have to write the state equations. So to write the state equations, we have, so here x1 dot, so we have x1, x2, x3, xn. These are the phase variables, and x1, x1 dot, x2, x2 dot, all these are the state variables. So x1, x2, x3, xn, and x1 dot, x2 dot, x3 dot, xn dot, these are the state variables. So these state variables, so x1 dot equal to dy by dt, and that is x2, because here x2 is dy by dt. So we can write here x1 dot equal to x2, and x2 dot equal to x3, x3 dot equal to, here it will be x4, and xn minus 1 dot will be xn. Now xn dot, so xn dot will come from this equation, because here now dny by dtn is xn dot. So this is xn dot, dn minus 1 y by dtn minus 1, this is xn, dy by dt it is x2, and here this is x1. So we can write xn dot equal to minus a0 x1 minus a0 x1 minus a1 x2 minus an minus 1 xn plus b0u, this term. So we have got the derivative of these variables x1, x2 and xn. Now we can write this in a vector form. So here so if this is, we can write x1 dot, x2 dot, x3 dot, xn minus 1 dot and xn dot, that is equal to so this is a matrix, and here we have the state vector. So x1, x2, x3, xn minus 1 and xn. Plus another matrix, because we have this u. So now we have to complete this matrix, because we have to write state equations. We have x dot equal to ax plus bu. So we are trying to write these equations into this form. So here we have state vectors x1, x2, x3, xn minus 1, xn, and this is the derivative of these state vectors. So here state vectors are x1 to xn, and the derivative of these vectors are defined here. Now we can write this matrix. So when we have to write x1 dot equal to x2, so x2 here is second, so second term, so here 0, then 1, then 0, then 0 and 0. So only the second term x1 dot equal to x2, and here it should be 0, because this equation we will obtain. Now x2 dot equal to x3. So x2 dot equal to x3, so here at the third position this element should be 1, others should be 0. Then x3 dot equal to x4. So here 0, 0, 0 and 1, and then here 0, 0. So x3 dot equal to x4. Now xn minus 1 dot. So xn minus 1 dot equal to xn. So here the last element should be 1 and the rest should be 0. Now come to the xn dot. So here xn dot, and of course here also zeros, because there is no any component of u in these equations. Now come to xn dot. So here we have xn dot equal to minus a0 x1. So this first element should be minus a0. Then minus a1 x2. So second element should be minus a1. And so on. So other elements like minus a2, minus a3, and so on. Then here minus a n minus 1, minus a n minus 1 xn plus b0 u. So here it should be b0. So what we see that these matrix, we can say this is A, these are the vectors, and this is B. So we have written this state equation. So this is its state equation. Now the output equation. So output, if we want the output, so we can write, because output is y. So this is the only output equation, and with this we have to represent as y equal to 1, 0, 0, 0, and here x1, x2, x3, xn. So this gives us in fact y equal to x1. So the same equation we have written as output equation in this form. So this is the output equation. So this is how a transfer function, if we have a transfer function, we can write this as a state equation and output equation. Now we will take one example and we will try to find. Now here one thing we can note that how these coefficients are shifting to this matrix, because other matrix there is 0 1 and 1, this is shifting. Now here in this matrix we have the coefficients of x1 is minus a0. So these coefficients are negative and reversed here. So the coefficient that was here, that is gone here, and the coefficient here is coming here. So coefficients are, so this matrix can be written by seeing this differential equation, because this coefficient is negative, they will be starting from this side, minus a0, minus a1, minus a2, and then minus a n minus 1. So let's take one example. So we have a transfer function. So this is input, this is the transfer function 24 by s cube plus 9 s square plus 26s plus 24. So this is the transfer function, and we have to represent this in a state space. So here first we have to find the differential equation. So we have, so it is like we have RT here, and here we are getting CT, and this is our state space vector x. So here let's first we find, so let's say that we have CS by RS equal to 24 by s cube plus 9 s square plus 26s plus 24. So this is, we have to find the differential equation. So we cross multiply this. So s cube plus 9 s square plus 26s plus 24, here CS equal to RS. So now we take the inverse Laplace transform of this and put the initial conditions 0. So here s cube, so we have C triple dot, because if we have this output CT, so C triple dot, because the Laplace transform of the nth order derivative is s power n. So s cube, we take the inverse, we will get C triple dot plus 9 C double dot plus 26 C. So here we have 26 C dot plus 24, here C equal to 24R. So here this is 24, so 24R. So we have obtained this is a differential equation we have obtained from the Laplace transform. Now we have to select the state variable. As we have to select phase variables as state variable. So we assume that here x1 equal to c is the output. So this is our state variable, and then subsequent, so we need third order differential equation, we need three state variable. So x1 equal to c, and then x2 equal to c dot, and x3 equal to c double dot. So here we have x1 equal to c. So x1 dot equal to, so let's write x1 equal to c, and x2 equal to c dot, and x3 equal to c double dot. So here x1 dot equal to, x1 dot is c dot, and c dot equal to x2. So we can write x2 dot. So we are here writing derivatives of the state variable in terms of state variable. So here x1 dot equal to x2, and x2 dot equal to c double dot, and that is x3, and then x3 dot. So x3 dot we can find from here this equation. So here x3 dot is c triple dot. So here this is x3 dot. So this is x3 dot, because x3 dot is c triple dot, and this is x3, this is x2, and this is x1, and this is r. So we can write x3 dot equal to minus 24 x1 minus 24 x1, so this is x1, minus 26 x2, and minus 9 x3, and plus 24 r. So now we have, so y equal to c equal to x1, this is output equation. So because here y output is c, and that is equal to x1. So now let's write the state equation. So here we have x1 dot, x2 dot, and x3 dot, that is x dot, and we have this matrix 3 by 3, and then the state vector x1, x2, x3 plus r. So here we have x1 dot equal to x2, so we have 0 1 0, and x2 dot equal to x3, so 0 0 1, so x2 dot equal to x3, and here it is 0 because there is no any r terms here. Now x3 dot equal to minus 24 x1, and minus 26 x2, and minus 9 x3, and plus 24, so here it will be 24 r. So here we can see that these elements are reversed. So here 24 is minus 24, this 26 is minus 26, and here it is minus 9 with negative sign. So now this is like x dot equal to ax plus bu, and this is the system matrix, and this is the matrix B, this one. Now the output equation, you can write y equal to 1 0 0 x1 x2 x3, because here y equal to x1 from this equation. So this is the output equation. So we saw that how we can convert a transfer function to state space. So we first take we write the transfer function with input and output. We take, with cross multiplying, we take this equation and we take the inverse Laplace transform with all the initial conditions 0, and then we get the differential equation. Then we select the state variables. So first state variable is the output. We select the output as the state variable. Here we selected the x1 equal to c was output, and then the subsequent state variables are the derivative of the first variable. So here x2 is the derivative of x1, that is c dot, so x1 dot, and this is the derivative of, so here this is the derivative of x1 dot, and this is the derivative of x2 dot. So we obtain this as state variables, and because in the state space equation we need the derivatives here, so we represent derivatives in terms of the state variables x1, x2 and x3, and here is this r is the input. Now if we want to represent this system as a block diagram, so how can we do? So we have this 24, so here into RT, here we have summing junction, we have integrator, we get x, so here we get x dot, then here we get x, here we have further integrator, so here we have from x3 we have to send minus this 9, so this is minus, then x2 we have to send minus 26, so we have here with minus sign, and then x1 we have 24, so here we have minus. So we can see here is the input RT with 24 RT we have input. Here we have x3 dot t, we integrate, so x3 dot t, so this is this equation, this is equal to, we have integrator, so we get x3t, and then we further integrate to get x2t. because here we can get, we integrate x3 dot, we get x3, and we integrate, we get x2. So we have, and then we integrate x2, we will get x1. So we integrate here this x2, we will get x1. So now this equation we have represented here. So minus 24x1 here, minus summing junction, minus 26x2 and minus 9x3, and this is plus 24r, here it is plus, and that is making x3 dot t, and y equal to x1t. So output is x1t, here yt or ct, whatever, we can write ct also. So this is how we represent this system. So this example we took from the book of Norman S. Nice, Control Systems Engineering. So I thank you for attending this lecture, and we will continue in the next lecture.